Greetings everyone, I'm Yunali from Seoul National University. In this presentation, I'm gonna talk about target visible polynomial trajectory generation with an MAV team. Let me begin my presentation. The contents are as follows. First, my research motivation will be introduced, and then I will present proposed method. Finally, I'm gonna show you our experimental results. Filming using drones have drawn a lot of attention from the public. However, even commercial drone, there are many cases that target becomes hidden by the obstacles when filming. This usually occurs because the drone takes a different topology path from a target. Therefore, in this work, drones try to avoid target occlusion by setting flight regions which are homotopic to target's path. There have been many researches about target tracing, considering target visibility. Some works proposed visibility metrics and used them as objective function of optimization. However, these attempts are not free from target occlusion. Also, in some works, their planners maintain target visibility as constraints. However, their planners utilize only small size of MAV and short duration target information. In this presentation, we propose a new target tracing trajectory planning algorithm. Our planner always guarantees all-time target visibility and can be used regardless of size of map. As mentioned earlier, our planner makes same topology safe flight regions with targets, and we call them homotopic safe flight corridor. Also, we eventually generate a piecewise polynomial trajectory that ensures that the target visibility is always guaranteed through only one quadratic program optimization. In this section, we explain our problem formulation. First of all, our MAV team consists of two drone agents. In camera agents, trajectory planner makes the trajectory which are free from target occlusion by obstacles. We assume followings. First, due to differential flatness of the multi-rotor dynamics, both agents use polynomial to represent their trajectories. Second, target agent shares its trajectory with camera agent, and the camera agents see target agent as starting point. We represent the trajectory with M-segment polynomial, especially with Bernstein basis. Therefore, our goal is to find control points that makes trajectory continuous, dynamically feasible, and collision-free and target occlusion-free. We formulate quadratic programming with following quadratic objective functions and affine constraints. First, we minimize the error to previous target's trajectory and derivatives of the trajectory. And first two constraints generate trajectory for a drone to move continuous and dynamically visible path. And last two constraints makes drone trajectory so that drones do not collide with obstacles and always see the target agent. From now on, I'm gonna explain how to make homotopic safe flight corridor. Target agent flies among obstacles, and its paths are shared to camera agent. To acquire topology information, we go through following process. First, parallel bidirectional rays are emanate from all obstacles, and we nominate the upward and downward rays with obstacle number and subscripts U and D respectively. Then we assign plus or minus sign to superscripts of letter depending on the direction in which the path traverses the corresponding rays. For example, we write a letter 1U plus because path crosses the ray from left to right, and we concatenate all letters and make a word. Based on the word, corridors are generated sequentially. With plus sign letters, we generate corridors on the left and upper sides of the corresponding rays, while minus sign letters make corridors on the right and upper side of the rays. By this rule, we can generate homotopic safe flight corridor. Additional generation process exists to address exceptional case. You can find the detail in our paper. In this section, we introduce how to set target visibility in quadratic programming. We use corners to define target visible regions. Corners are defined as vertices of rectangular bounding boxes of obstacles, and we can easily find it because the points are intersection of two consecutive corridors. Visible regions are defined depending on the direction in which drum moves around obstacles, and they are colored in red and blue in this slide. And these regions can be represented as linear constraints. As we mentioned earlier, we use Bernstein basis in trajectory planner by using the property that products of two Bernstein polynomial is also Bernstein polynomial. Whole visibility constraints can be expressed in Bernstein polynomial form. And we know that Bernstein bases are non-negative during defined time interval, so we make all coefficients be non-negative so that inequalities are satisfied. Since we generate target trajectory with piecewise polynomial and use safe flight corridor, we need to have time allocation process and make time nodes which split whole time duration. Time allocated for each corridor is the staying time from the corridor intersection to the next one. We can acquire intersection points numerically by adding and subtracting the quarry time d tau and its halves. By this process, we could analyze target's trajectory and get staying time information. Figure shows an example. Then we are gonna make time sequence for optimization. First, we have target trajectory information. With aforementioned methods, we get staying time of target agent in each corridor. In our work, we set the time during which an agent stays in each corridor is equal for both agents. So we set the time duration for camera agents to stay by delaying the smallest value of corridor time interval that is obtained earlier. Our strategy makes the two agents stay in the same or consecutive corridor throughout the entire flight. Gray shaded time intervals are when the two agents are located in consecutive corridors, and white time intervals are when two agents exist in same corridors. And we use previous target agent's trajectory for camera agents to follow target agent. With these time nodes sequences, we can split times into multiple time intervals for whole time duration, and in the backend optimization, M segments polynomial will be optimized. Back to our optimization problem, we can formulate the optimization problem to quadratic programming. Our objective function can be expressed into quadratic function, and all constraints can be represented into affine inequality and inequality constraints. To sum up, this formulation are quadratic programming problem and can be solved by conventional convex solver. This video shows the simulation results for two virtual environments. First simulation is 90 seconds flight and the second one is 24 seconds flight. Regardless of complexity and size of map, the optimization is solved by single quadratic programming solver. In the first simulation, we compared our method with the visibility metric approach. Visibility approach failed to track targets consistently, but our method succeeded in maintaining target visibility. Also, our method shows much more smooth and gentle flight. Also, we conducted a flight test with two Crazyflie quadrotor. We use QP-OASIS solver to solve optimization, and it takes 20 milliseconds to generate trajectory. As you can see in bottom video, target agent is always visible to camera agents during the entire flight. In conclusion, we presented target visible trajectory generation method that ensure target visibility for all flights. Safe flight corridor generation method using topology concept is proposed. The backend optimization addressed the entire flight, which is target visible by solving a single quadratic programming, regardless of size of map. Thank you for listening to my presentation.